Modeling Hopf solitons with elastic rods.
Thanks to the organisers for the chance to talk to you all today. The work I'm going to describe today is really a connection between. I'll start again. So the work I'm going to describe today is really a connection between two different areas, both of which have featured in this conference. So the first area is the area of the idea of classical field theories, and particularly solitons and topological solitons in those theories. The second area, which we heard a lot about over the last couple of ideas, is looking at knots and energies for knots. And the idea of this talk is just to show you some ways in which these are related, and ways to convince you that the relation is actually a useful tool for comparing things and understanding things. So I'll start just by telling you what the field theory I'm interested in is. This is the field theory. It's called the Sturm-Fedayef model. You've seen it a couple of times this morning. It's a field theory whose field content is a map phi from R3 to S2. You can think of that as having three components, phi1, phi2, phi3, whose norm is equal to 1. And everything you want to know about the statics of this theory is encoded in an energy functional, which I've just written up for you on the slide here. So you'll notice that there's three terms in this energy functional. There's this so-called sigma model or Dirichlet term. That's a well-known component of an energy function. It's related to harmonic maps and has many physical applications. The second term, the so-called Sturm-Fedayef term, you'll notice rather than being quadratic in derivatives is quartic in derivatives. And the fact that it's quartic in derivatives means that you can have stable solitons with non-zero energy in this model. The last term in the model, which I've said is optional, some people study its effect, but you can study the model without it depending on what you're trying to model, is this so-called mass term. So the first thing to notice about this model is it has a lot of symmetry. In fact, if you ignore that term, then both of these terms are invariant under Euclidean transformations of R3 and also under rotations of the target space. You can add dynamics to this model. I haven't told you how to on this slide, but the nice thing is the dynamics are sensible. And in fact, if you just look for models with terms quartic and quadratic in derivatives with sensible dynamics, this is the only model that you can use. So it's kind of uniquely fixed by its symmetries and by having sensible dynamics. So the first non-trivial fact about this model is that it has a conserved topological charge, which is related to the third homotopy group of the target 2 sphere. So there's a few different ways to understand what that charge is, and I'll try to sketch those for you now. So if you think of your field as a map from R3 to S2, here's the 2 sphere, and here's R3. Well, you can look at the pre-images of 2 points on the target sphere, say a point here and another point here, and the pre-images of those points in R3 will both typically be curves or collections of closed curves. So if you draw them both, then normally what happens is that they're linked, and the linking number of those two curves is equal to this Hopf degree. There's another point of view where you can think of this Hopf degree as a kind of helicity, but because it's related to the map into the 2 sphere, it's unlike usual helicity, it's exactly conserved for topological reasons.
Why would it closed curves?
boundary condition.
Which
Yeah.
one?
Well, you impose the condition that the field goes to a constant at infinity. So unless you choose that value, every pre-image will be bounded away from the.
But that turns
Yeah,
to
it-
compactifies to a free sphere. On R3, they don't have to be.
Yeah,
It's the same thing.
it can't happen that the curves are not closed just because it's coming from a map into the two-sphere, the way it works. Okay, so the first interesting question in this model is, given that we have this topological charge, then for any given value of that charge, what are the minimal energy solutions of the equations of motion? What are the critical points? So that's actually quite a difficult question. This model was invented in the 70s by Faddeev, but it was only in about 1997 that people really had any idea what the critical points of the energy function look like. So, well, the way to determine that is just to do lots of numerics, and this is a result of numerical simulations shown for you on the slide here. So all of these different shapes that you see are the energy minimizers in different topological classes. And what's plotted, if you look closely, there's a light gray tube and a dark gray tube very close to each other. Well, those correspond to the green curves and red curves in my picture over there. And if you wanted to, you could look at these pictures and check for yourself what the topological charges are. So, for example, this one in the top left corner, the light grey tube links with the dark grey tube once, so it has Hopf degree 1. So, if you look at all these different solitons, you'll notice that they're all quite distinct from each other. They have different shapes and different knot types. For example, the first two, the light grey tube is just a ring lying in the plane. In the third one, with charge 3, you have a tube, but it's somehow buckled out of the plane. And as you go to higher charges, you get exotic things like links, and eventually at charge 7, for the first time, the energy minimizer is a knot. So, as I said, these results just come from numerical simulations. Before we started this project, no one really had any qualitative idea why this should happen. We just know it happens because doing a lot of expensive numerics tells you that that's the case. So the idea of the project was to try and get a bit more of a qualitative feel for what's happening. So this is the idea we came up with. We came up with an elastic rod approximation. So, now I'm going to introduce an elastic rod model, and this is going to be turn out to be a nice description of the solitons. So, well, what's in my elastic rod? Well, first of all, I have a blue curve in position space. I can parameterize that by a parameter sigma, and that's going to describe the center line of an elastic rod. And in addition to that, I'm going to have a normal vector m moving along the curve, just pointing outwards, and that lets me describe twisting. So the twisting of that vector is what's going to give me the charge in the original model. You'll notice that this also has a thickness rho. That's to model the idea that two different pieces of the rod can't get too close to each other. And the energy function that we use for these guys is this one written in here. It has there's 3 contributions to the energy of a rod. First of all, there's a stretching energy, which is just measuring the length of the rod. So a longer rod will have a bigger stretching energy. We have a bending energy, which is related to the curvature of this rod. And finally, there's a twisting energy, which measures how the normal vector m twists as you move along the rod. So putting all these three terms together and giving them coefficients A, B, and C defines a simple elastic energy for rods. Now, so some of you work on tight knots. Well, if I only had the first term, this would just be measuring the length of the knot with its radius fixed. So in one particular limit, this reduces to studying tight knots. But equally, if I ignored the A term and just had these two, then this would be Kirchhoff's energy for elastic rods. So somehow this model is a mixture between studying tight knots and studying Kirchhoff elastic rods. Now there's three parameters in this model, A, B, and C, but actually two of those just correspond to choices of units. So really this is a very simple model. There's only one dimensionless parameter, which is this ratio C over B. So that's the only degree of freedom we have in this model. That's the only thing we can play with to fit to the whole spectrum of knotted solitons. So then the question is, does this really work? So the first thing we did was just to look at solitons on R3. In other words, to look at the pictures I showed you a couple of slides ago. So I've just reproduced the first three of those pictures on the left of this slide. So this is charge 1, this is charge 2, and this is charge 3. And those of you, again, that know about Kirchhoff rods will recognize this as a familiar pattern, because in Kirchhoff elasticity theory, if you take a length of elastic rod, join it up into a circle and add a twist, then depending on how much twist you have, that could either remain in the plane or buckle out of the plane. This is Mitchell's famous buckling instability for elastic rods. So then we can use that information to tell us how to fit the elastic rod model to the solitons. So this is how you do it. There's a well-known formula for the critical twist in Kirchhoff's elastic rod model, and we know from the field theory that twist has to be somewhere between 2 and 3 twists. So that gives a very tight constraint on the only free parameter that we have, and so now we just have to make a choice for that parameter in that interval, and in fact we just made one choice. We didn't really play with this at all, so we've just now fixed the one remaining parameter in the model, and now we have to see if it fits with everything else. So now this graph is just comparing the spectrum of elastic rods with the spectrum of solitons in the field theory, and the different shaped dots correspond to different configurations, to knots, links, and unknots, and so on. And it turns out for charges 1, 2, 3, 5, 6, and 7, the minimum energy thing in the rod model has the same type as the minimal energy thing in the soliton model. The only exception is at charge 4, where actually the minimum thing in the soliton model can't really be captured in the rod model, but we do get the second lowest state. So just to bring that to life, these are some pictures of the configurations in the field theory and the configurations in the rod model, and you can see for all the charges I've shown you, we have the same topological type in both both models, and the shape is they're at least on similar length scales as well.
So again, what is the Hopf number in this case?
So if you're in the rod model, you have a curve defining the center line of the rod, and you have this normal vector. So if you add an extra curve that's using the normal vector, it's the linking number for those. So a completely natural definition. So this seems to reproduce known results in the soliton theory. So let's look for some new things. Well, this is something I did with David Foster, who's also here. You can ask him about some of the simulations related to this if you want. The rod model makes a simple prediction about solitons on the space R2 cross S1. So if I impose periodic boundary conditions in the Z direction, then I can change the length of those periodic boundary conditions. That's varying a parameter P. And as I decrease P from large values to small values, I go through various buckling transitions. So at very large lengths, when the rod is stretched out, I have just a straight configuration. At some critical length, as I relax it, it will buckle to form a helix, and as I relax it once more, it will buckle again and form this kind of coiled configuration. So the rod model predicts that that should happen, and then we spent quite a while testing that in the field theory. So I'll just show you the pictures that we got from the field theory. So this is what happens if you have one twist in the Z direction. We've got the rod model on the left and the field theory on the right, and you can see that they're both staying more or less straight for this particular value of twist. If you put two twists in, then you get buckling in both the rod model and in the soliton model. And if you put three twists, you get a second buckling. So you can see that this rod has buckled again so that it has no continuous symmetries. And in the field theory, well, actually at the same period we found two configurations. One has a helical shape and one has no continuous symmetries. As far as we can tell, within numerical accuracy, these two configurations have the same energy. So we don't know which of these is the minimum, but this one corresponds to this state in the rod model. So I think we wouldn't have found this one without knowing what to look for. So that the rod model has told us to look for something which probably we would have missed if we'd been using more conventional methods.
In fact, there are simulations of heat or inter in Faddeev's curve model with periodic boundary conditions, and they show exactly twists like that.
Right. So Inter looked at a different set of charges to us, and I think he didn't. So what we've done is found, the exact period where buckling is supposed to occur, and we've done it in very simple cases with low charges. Inter has done some simulations, but they're of a different regime, and certainly he doesn't talk about buckling transitions. So just the last thing to mention is that you can add dynamics. I won't bore you with the details of how to do that, but if you add dynamics in the rod model, you get a simple prediction for how energies scale with charge. That's not the topological charge, but a kind of electrical charge. So this is just showing you that, well, in this ongoing work, we've got red curves predicted by the rod model, and then these green curves have been the result of a lot of numerics with Martin Spate and Juha Jauka and Jascha Schneer. And you can see that, well, the field theory is again doing what the rod model says it should do. So that's the end of the talk. We have a simple model for solitons based on elastic rods. It seems to have good predictive power. We think this is going to be a useful tool for constructing new solitons. And, well, there's still more to go. So I think the idea of using elasticity theory to model solitons and things in field theory in general seems to be a productive idea. So I think this could be extended to other field theories. Right, thanks for your attention.
Question?
In the theory of elasticity, the conditions on the ratio of BC, bending to stiffness ratio, come from some more general Nicolai conditions. But I think that, as I understand, there are no such conditions in your model. So it means that they are completely free to...
Well, the parameter is a free parameter in the rod model, but I mean, we just picked one value for that, and that's the value that seems to work.
But I think, why did you take this parameter, which actually which came from the very narrow interval?
Right.
And this narrow is because of elasticity. So you don't this constraint, so you're not restrained to take parameters from this interval.
Well, if we want a useful model, then we are constrained to take values there. The idea is to develop a useful model for solitons, and the range of values for that parameter which are useful is very small.
So you just want to map your model to the real,
Yeah,
more
we're trying to
physical objects, or
yeah, we're trying to find a simple model that captures everything that happens in a more complicated model, and there's just a small range of values for that parameter which are able to do that.
One more question.
Me?
Go ahead.
Right. So,
Yeah.
so can you derive this Roth model as some effective theory starting from the, so Martin is laughing, it's probably a naive question, starting from the Lagrangian, from
Well,
the Padiev.
So there is a way to obtain this. This was Martin's idea. You can, starting from an elastic rod configuration, you can construct the field phi and plug that into the field theory as an ansatz. That will give you an energy function for elastic rods. Actually, the energy function you get that way has a lot more terms in the model than the model I showed you here. But amongst all the terms in that, these three simplest terms are part of it. So there is a way to derive it. Yes.
Thank you very much, Derek.